Okay, so now what we want to talk about is the situation where we don't drop a ball from some height, but we stand on the ground and we toss a ball straight up into the air. Well, if I can draw a straight line, straight up into the air, and then it comes right back down into our hand. Right? That's the situation we now want to talk about. Now, here is where the difference between vectors and scalars plays a large role, right? Vectors versus scalars, okay? Here's where this really starts to come into focus for our purposes, right? So, first things first, let's start with a situation and then work through it step by step, right? So let's just use the situation the book has, right, in figure 310, right? So we have a ball and we toss it up with an initial velocity of 20 meters per second, okay? And we want to know a few basic things. The example, and we'll go through a few of the calculations. The example goes through what happens at each second of flight, right? So after 1 second, how high is it and what is its speed? After 2 seconds, how high is it and what is its speed, etc., etc., etc. And we will do those, but the big questions with problems like this, okay? The big questions with problems like this, some of the things that one might be able to ask are, if I know what the initial velocity is, what might be the maximum height? That the ball might reach, right? So what's the maximum height for the object? And that might be one question. And then a second question that's very popular to ask is, what's the total flight time? Or what we would call the total time of flight, right? And so these two are what we really want to know. Or, vice versa, okay, if I know the total flight time, can I get the velocity it was launched with, and can I get the maximum height? Or if I know the maximum height, can I get the velocity and the total flight? And it turns out the answer is yes. If I know one of these, I can get the others. Some easier than others, and some it takes a little more work to get, but I can do it, okay? So we'll do this example here, and we will look at the situation, and we will erase these and go through this step by step, all right? So what we want to do is follow the figure in the book, figure 310, and just look at this object, its path at intervals of 1 second, okay? So we know it's going to go up, and then it's going to come back down, all right? So, and again, when it's thrown up, that's at t equals 0. So at t equals 1 second, what's the velocity? And what's the distance, or the height? Right? Okay, so I said before, right, this is where we need to take the whole vectors versus scalars into account. So remember that acceleration is a vector, as is velocity. So when you toss an object up, what direction are these vectors pointing in initially? Okay? Well, it turns out that to kind of describe this type of motion, it pays to define your coordinate system. Okay? So when we're talking about a coordinate system, essentially we're talking about a way to define positive and negative. And if you're only moving in one direction, i.e. up and down, as opposed to up and down and side to side, then we only need only need to define one direction as positive and one direction as negative. Now, it's customary, but you don't have to, okay? It's just customary to make the direction that your initial velocity in to be positive. Right? So I'm going to make the upward direction to be my positive direction. Okay? And the downward direction is therefore going to be negative. So what is my initial velocity going to be in this case? Is it going to get a plus or a minus sign? Well, since my initial velocity is upward, I'm throwing it upward, and that's what I've defined to be as positive, then my initial velocity gets a positive sign. Okay? Now, what about my acceleration? Well, acceleration always acts downward. Okay? Acceleration always acts downward. So during these equations, A will get a negative sign. And in fact, not only will A get a negative sign, A will be G. Okay? Because we're in free fall, as soon as I let this ball go, I'm under the assumption that air resistance is negligible, and therefore gravity is the only thing acting on it, so we're in free fall. So in fact, our acceleration will be in fact G. So our acceleration is going to be negative G. Okay? Alright, so with these tools now, and with this knowledge, we can now start to compute what's going to happen at each step of the way during this object's flight. Okay? So at t equals 1 second, we know that our acceleration is going to be negative g, and we want to know the velocity and the distance. Okay. So now remember that velocity, not initial velocity, but final velocity, is equal to initial velocity plus at. But a equals negative g, so this is going to be v0 minus gt. Okay? Now, to kind of get a sense of what this physically means, we're starting off with an initial velocity in the upward direction, but our acceleration is downward. So this is going to cause the object to slow down, which is what an object on its way up does. If you notice very carefully, you throw an object up, it will slow down until it reaches its maximum height, and then it'll speed back up on the way back down. Okay? But for on the way up, this is the equation we must use. Right? So this is going to be, and our initial velocity was 20 meters per second minus 10 meters per second squared times 1 second, and 10 times 1 is 1, or 10 times 1 is 10, and 20 minus 10 is therefore going to be 10 meters per second. Okay? So after 1 second, let's say it's right here after 1 second, then its velocity will be half of what it was before. Okay? So down here, our velocity was 20, and right here, our velocity is going to equal 10. Okay? Alright, so what about the distance it's covered? Well, here we do need to take the initial velocity into account because that's, we have it, right? It was 20 meters per second. So this is going to be 20 meters per second times 1 second minus 1/2 gt squared, right? And again, the minus sign is because g is negative. G is pointing downward. And so this is going to be 20 meters per second times 1 second minus 1/2 times 10 meters per second squared times 1 square seconds, or 1 second's quantity squared. Now again, 1 squared is going to be 1, second squared is going to be square seconds, and so our square seconds is going to cancel out with our second squared in the bottom there, and 1 times 10 is 1, times 1/2 is 5, so 20 minus 5, the total distance we've moved up is 15 meters. So after 1 second, right, now we're counting this as the 0 line. Alright, we're counting where the ball left our hand from as the 0 line. So from this 0 line up to here, it went up 15 meters. Okay? Now, what about at t equals 2 seconds? Right? What are the velocity and the distance? Okay, so the velocity is going to equal v naught minus gt. So this is going to be 20 meters per second minus 10 meters per second times 2 seconds. And, meters per second squared there, apologize. And so, what we're going to get is 2 times 10 is 20, and we have to subtract that from 20. So this overall thing is going to be 0. Ooh. Okay, so here's an interesting point, right? This is what's known as the turning point. At this point, this is when the object ceases to start moving up and then starts to move back down, okay? And an interesting thing about this point is exactly this. The velocity is 0. So at the maximum height, the velocity is 0. Okay? That's a very important feature of projectile motion. Okay? So at the maximum height, the velocity is going to be 0. And what about the distance? The distance equals v naught t minus 1/2 gt squared. So v naught, again, is going to be 20 times 2 seconds minus 1/2 times 10 meters per second squared times 2 seconds, quantity squared. So this is going to be 40 meters per second minus, well, 2 squared is 4. 4 times 10 is 40. You cut that in half and you get 20, and our second squared are going to cancel out with our second squared. Oops, I'm sorry. Our second squared here is going to cancel out with our second squared here, and this should just be meters. Right? That should just be meters. Apologize. And we said this was going to be 20 meters. So it will have gone up a total distance of 20 meters. Right? So, because this is the point where the velocity is 0, 20 meters is the maximum height. And you can convince yourself of that. I won't do it, but you can convince yourself of that. If you take t equals 2.1 seconds, okay? If you take t equals 2.1 seconds, just a split instant later, right, then you should, if you calculate d, it will be less than 20 meters, meaning that it'll be lower to the ground or closer to the ground. So this 20 meters is the max height. And again, I cannot emphasize this enough. I cannot emphasize this enough. The max height is where the velocity is 0. Okay? So, if you continue to do that process on the way back down, okay, you would see that, well, let's just look at t equals 4 seconds, okay? And why do I want to look at t equals 4 seconds? Because projectile motion has a very interesting feature, and that is whatever the time it takes to reach the top of the trajectory will be the time it takes to reach the bottom of the trajectory. So if I leave right here and I arrive right here, at this point right up here, it'll take just as long to get up there as it will to then get back down. Okay? So let's look at the velocity and the distance at 4 seconds, which should be the total time of flight. All right? So if we calculate the velocity at 4 seconds, what we're going to get is 20 meters per second minus 10 meters per second squared, and I'm going to have to erase some of this. All right. 10 meters per second squared times 4 seconds, and 20 meters per second minus 40 will be negative 20 meters per second. Okay? And this is a very interesting thing. Okay? Now, this negative sign indicates the direction, right? So remember before we defined up as positive. Because this velocity is negative, that means it's pointing downward. But it has the exact same magnitude, the 20 meters per second, as you launched it with, right? So if you launch a ball up with some velocity, it will come back down with that exact same magnitude, but in the opposite direction. Another way of saying this is that whatever speed you toss it up at will be the speed that it then hits your hand with, okay? But, of course, the direction of motion will be opposite. In one case, you're tossing it up, and in the other case, it's coming back down. So the velocities are different because they have different directions, but their magnitudes are the same. Okay? Whoops. My pen cap just dropped. Okay, so now let's look at the distance calculation, and hopefully you have a sense of what this should be. So the distance is going to be v0t minus 1/2 gt squared. And what do you predict? Well, if we call this the 0 point, right, this is where it left our hand from, and it's coming right back down to that point, the distance between these, or the distance between these two levels is 0, so we should get a distance of 0. When you toss something up from your hand and then it comes back down, if it's in your hand, then it's at the same height that it originally started from. So the total distance should be 0. So let's see if that's true. So 20 meters per second times 4 seconds minus 1/2 10 meters per second squared times 4 seconds quantity squared. Right? So our first set of factors will give us 80 meters. I keep wanting to write meters per second, but it's going to be 80 meters. And 4 squared will give us 160 square seconds. And that times 10, or I'm really jumping the gun here. 4 squared is 16. 16 times 10 will be 160. And our seconds squared will cancel out with our seconds squared. So we're left with meters. And 60 times 1/2 is going to be 80. So 80 minus 80 we do in fact get 0. So we see that after 4 seconds, the object has returned to the exact same height that it was initially. Okay, so that is the way to determine essentially the entire trajectory. Now, the two questions that we asked earlier, okay, let's kind of go back to them just to remind ourselves of what they were. Oh, I erased them. That's right. My bad. I'm sorry. So those two questions were time of flight and max height. Okay, so for any given arbitrary velocity, and let's just do an example that's different from the one we did, and I'll show you how to get both of these from that information. Okay, so let's say that we have an initial velocity of 10 meters per second. Okay, and we want to know. So this is the case where we toss it upward with an initial velocity of 10 meters per second, and we want to know what its max height is, and we want to know how long it's going to take to complete the total trip. Okay, so how do we do it? Well, it can be done a couple of different ways. Okay, but remember what I said, the flight is going to be symmetric. Okay, the flight is going to be symmetric. So what I can do is use the fact that at the top the velocity is going to be 0. Okay, so at the top the velocity is going to be 0. So if I go back to my equation, v equals v naught minus gt, okay, v equals v naught minus gt, at the top I know that my velocity is going to be 0. So I can get 0 equals v naught minus gt. And I can solve this for t, and I'll get gt equals v naught, and then t equals v naught divided by g. So this is going to be 10 meters per second divided by 10 meters per second squared, which will give me 1 second. So it's going to take 1 second for it to get from here up to here, which means that if it takes 1 second for it to go from here to here, it's going to take another second for it to go from here down to here. So the total flight time is just going to be twice the initial velocity divided by gravity, or in this case 2 seconds. Okay, so now we have the total time of flight, and we're also in a position to calculate the maximum height. We know that the maximum height occurs where the velocity is 0, and I just showed you how to calculate where that time occurs. It occurs in our case at 1 second. So if I calculate the distance that it's traveled after 1 second, that'll give me the maximum height. So distance going to equal v naught t minus 1/2 gt squared, which is going to be 10 meters per second times 1 second, minus 1/2 times 10 meters per second squared times 1 second's quantity squared. So we're going to get 10 meters per second minus, well, 1 squared is 1, times 10 is 10, minus 5 is 5. I've been doing this the whole video. I apologize. This is just 10 meters. And again, our square seconds, and our square seconds are going to go away, so it's going to be 5 meters. So after 1 second it will have gone up 5 meters, and that is what our maximum height will be. Okay? So it would have gone up a distance of 5 meters, or roughly 15 and maybe a third feet. Okay, maybe even closer to 15 and a half. But it'll be really close to 15 feet. Okay, maybe even closer to 16, but who's counting? So that gives you the way to calculate the maximum height and the total time of flight. Okay? Okay, so the last thing that I want to talk about is actual projectile motion. Okay, and this is the case where you're launching something at some angle. So let's say if you have a cannon and you launch a cannonball and it follows a trajectory like this. Okay, so this is where vectors also come into play very importantly, because whatever angle you initially launch your ball at with respect to the ground, okay, what we can do is break that initial velocity up into its horizontal and vertical components. So if this is your initial velocity, this would be your initial velocity in the x direction, this would be your initial velocity in the y direction. And in fact, actually analyzing this motion is going to be a bit beyond what we do in this course, but I just want to tell you a few certain things about it to make you more familiar with it. First things first, the maximum height and time of flight are found the exact same way that you did before. It doesn't matter now that we're launching this and it covers some horizontal distance now. Okay, the maximum height and the time of flight are the exact same. But you must only work with the velocity in the y direction, the up-down velocity. Okay? Because it is this direction, the up-down direction, that gravity is working. So gravity always acts down, just as in the other case. Okay, and so because of that, it's the velocity in the y direction that you need to plug into the equations that we did in the previous examples to find the maximum height and the time of flight. The velocity in the x direction doesn't change. Okay, that velocity doesn't change because there's no acceleration. So if I were to look at this, let's say I've launched something and its path looks like this, and I look at it at different times throughout the flight, and I draw arrows indicating both its velocity in the y direction and the velocity in the x direction, right? So at this point right here, its total velocity is going to be something like this, meaning its x velocity will be right here, and its y velocity will be right here. At each of these points, my x velocity will not change, so the length of these arrows won't change. But what about the y velocity? Well, you can tell that the y velocity is going to get shorter and shorter, and then up here it's 0. So at its max height, the velocity in the y direction is 0, and then it gets smaller in the negative direction, or it gets larger in the negative direction, I should say. Right. And so this is how you would actually analyze the motion of an object. And here's a bit of trivia, all right? What angle, if you ignore air resistance is optimal to launch something the farthest for a given speed. Okay, and I'll let you chew on that one for a little while, then I'll give you the answer on Blackboard. All right. I will see you next time, and we are done with Chapter 3. In the next video, we'll start Chapter 4. See you then.